So I think we can start. Welcome back. Last time we looked at how to use invariant set theorems to look at convergence to different kind of final behavior. And we looked in some detail at an example of convergence to limit cycle and showing how we could show global convergence to a limit cycle by applying first the global invariant set theorem, which was telling us that we converge to the limit cycle or to the origin, and then on top of that applying the local invariant set theorem, which told us that unless we started exactly at the origin, we actually converge to the limit cycle. So this was an example of using these invariant set theorems not just to get rid of technical questions about when power stops being dissipated, but also to analyze convergence to more general forms of final behavior. We then talked about how to find Lyapunov functions, and we said, in general, these theorems don't tell you how to come up with the Lyapunov function candidate or the LaSalle Lyapunov-like function candidate. There's a particular case where that's very easy and that's very systematic. It's the case of linear time invariant systems. Okay? And we said, well, that might sound like, a big deal kind of remark, right? Because, of course, we don't need this to study linear time invariant systems. But we said there were two main reasons to do this. Okay, one, of course, is that it gave us a common language to talk about both linear and nonlinear systems. But more practically, because as Lyapunov functions, like energy functions, are going to add as you pile up, subsystems, it's nice to have if you have part of your system which are linear, whether it's in the controller or in the system dynamics itself, it's nice that they come up automatically with their Lyapunov function block. Okay? So that's why we were interested in deriving Lyapunov functions for linear systems. So we had started doing this after a brief review on matrix algebra. So remember, the idea was to say, okay, so what we're going to do is we going for a system x dot equal ax, linear time invariant system. We're going to look for a Lyapunov function to describe the stability of the system. Of course, we'll be able to do that if this system is stable. And the Lyapunov function, we're going to look in the form of a quadratic form, so x transpose px, where p is a constant, symmetric, positive definite matrix. And so this, of course, this v, therefore, is a globally positive definite function, right? Because, of course, P is positive definite. P is a positive definite matrix. And, of course, V tends to infinity as x tends to infinity, also because P is a positive definite matrix. Remember, we said if you have something like x transpose Px, it's going to be lower bounded by lambda min of p x transpose x, right? We said that in the general case. And therefore, since p is a positive definite matrix, this lambda min is going to be strictly positive, okay? And therefore, x transpose px will tend to infinity as x tends to infinity, okay? So using this bound on x transpose mx we talked about last time. Okay? So if we apply it here, using this left part of the bound, we get this, and this is strictly positive, and therefore this second radial unboundedness property is going to be verified. Now, if we look at v dot, we find as we did last time, 3 terms, okay? So x dot transpose px plus x transpose px plus x transpose p dot x plus x transpose px dot. P dot, of course, is 0 because p is constant, and x dot is equal to ax, that's the dynamics. So we find that this gives us x transpose A transpose P plus PAX. Okay? So at this point, we have our linear, strictly stable system. We've taken a guess at what the Lyapunov function candidate could be. Okay? We picked a quadratic form, you know, perhaps motivated by things like LQ or something like that. But anyway, that was the guess. We differentiated this. Differentiated the product, okay, so we get 3 terms. And we replace x dot by ax, and we get this, okay? So this said, at that point we said, okay, so this matrix in the parenthesis we're going to call minus q, okay? So in other words, given a p, I define Q by this equation, which incidentally it's called the Lyapunov matrix equation. And one plausible question is, you know, suppose I choose a P here which is positive definite, let's say identity, right? Then if the system is stable, is it true that the corresponding Q is positive definite? Right? If this was true, of course, if you could say, well, you know, you pick an arbitrary P, for instance, identity, the corresponding Q given by this equation is positive definite if A is stable. Okay? Then, of course, this V dot would be globally negative definite, and you would be done using the global Lyapunov theorem for asymptotic stability, right? So the question, therefore, is I'm going to rewrite here this Lyapunov matrix equation. So A transpose A, P plus PA equal minus Q. I start with a symmetric positive definite matrix. Does it imply that Q is also positive definite? Okay. Well, first of all, it's very easy to see that, of course, Q is symmetric. Okay? Q is symmetric because if you take the transpose, you get A transpose, P transpose, but P is symmetric, so A transpose P plus P transpose, which is P times A, right? So Q is symmetric. So that's okay. Okay. But however, it's very easy to show. You just have to pick up a counterexample. There's one in the book, okay, a 2x2 counterexample, that this implication is not true. All right, so as I said, you know, in math you have to be lazy and you have to be, you know, optimistic, right? But actually that was a little too simple. Okay, that was a little too simple an assumption. But if A was strictly stable and you picked an arbitrary positive definite P, then you would get a positive definite Q. All right? So that's not true. But not all is lost, right? Because what this calculation says, somehow, given a strictly stable system x dot equal ax, we need to find a pair of matrices, a pair of symmetric matrices, P and Q, which are both positive definite. Okay? So what turns out to be true is that the converse is true. In other words, if you start with a symmetric positive definite matrix Q, then you can solve this equation. Of course, it's more complicated than, you know, just computing Q from P, right? But you can solve this equation. This equation has actually a unique solution. And if the system x dot equal ax is strictly stable, this unique solution P will be positive definite. Okay? So it's not quite as simple as it could be, but it's not that bad. Okay? If I see this equation not as defining Q given P, but as defining P given Q, then I'm all set. I have a pair of positive definite matrices if A is strictly stable. All right? So that's what the theorem says, okay, and it's proved in the book. It's not very hard to prove, but so given any constant, right, Q equal Q transpose positive definite, for instance, Q equal identity, which is the simplest choice, there is a unique solution P to the, let me call it LME, the Lyapunov matrix equation A transpose P plus PA equal minus Q. If the system x dot equal AX is strictly stable, actually, back up a second. Given any Q positive definite, there's a unique solution P to the Lyapunov matrix equation A transpose P plus PA equal minus Q if the system x dot equal AX is strictly stable. This solution can be written P equals sum from 0 to infinity of E transpose AT times Q times E transpose AT. So this is a matrix exponential, right? It's the exponential of the transpose of this matrix. This is the matrix Q, and this is e to the at. Okay? So that's what the theorem says. You know, if you start with a stable, strictly stable linear system, x dot equal ax, then this Lyapunov matrix equation, given some positive definite Q, has a unique solution P, right? Which, by the way, can be computed this way. Okay. Now, how do we see, by the way, even if we haven't shown this theorem, again, it's, you know, it's half a page in the book, right? It's not a big deal. Even if we haven't shown this theorem here, how do we see where the fact that A is stable comes in? Well, because you have this infinite integral, right? So even if you take a scalar system, right? Suppose you had x dot equal 2x, right? Then this infinite integral would be blowing up on you. You wouldn't have a constant matrix P, right? So the very fact that we can write this is fundamentally using the assumption that A is stable, right? So that these basically are decreasing exponentials. All right? So that's what the theorem says. It doesn't work in general from left to right. In other words, given P, symmetric positive definite, Q in general is not necessarily symmetric positive definite. The converse, though, is true. If you start with a symmetric positive definite Q, for instance, Q equal identity, then this equation, this Lyapunov matrix equation, has a unique solution, P, which incidentally can be written this way. And this unique solution is positive definite. Okay. Which, of course, can be seen directly from the way it looks, right? Because basically it's a square, right? So this solution P is symmetric and positive definite. Okay. Everybody understand what this theorem says? Right? Given a strictly stable linear system, given Q, for instance, identity, you can always find P, the unique solution of this equation, and that P will be symmetric positive definite. And happens to be written this way. Now, in the same way that we said, the definition of a Jacobian is df over dx, right? But in general, that's not how you're going to find it in the vicinity of a particular equilibrium point. What you're going to do is neglect higher order terms. Similarly, this is a theorem which is useful to prove things, right? But if you need to find P, there's a faster way in general. Okay? And which is the faster way? Which is just to solve a set of linear equations. Right? You know that P exists and is unique, right? So the same way that you knew the Jacobian existed and was unique, right? So you know P exists and is unique, so you can just solve this equation. You start with Q equal identity, and you solve for P, right? How many equations is that? Three. Yeah, so three, because if P is 2 by 2, in general, yeah, it's ln plus 1 over 2, right? Because it's a symmetric, Q is a symmetric matrix, right? So you only have to take basically half of these equations. Right? So this is the general result. In practice, especially if you do a little exercise by hand, right? You pick Q equal identity and you solve, this set of equations, and of course you solve basically only half of them because everything is symmetric. Okay? Questions about that? And of course you'll do that in the homework as well. Okay. Questions about that? All right. So basically that gives you a completely systematic way to take a linear, strictly stable system and come up with a Lyapunov function for it. And a Lyapunov function in the strict Lyapunov sense, no need of the invariant set theorem, right? In the strict Lyapunov sense of global asymptotic stability. Okay? Questions? Okay. So what I'd like to do now is up to now we've been looking only at systems x dot equal f of x, right? Autonomous systems, including in this linear case, okay? So now I'd like to look at non-autonomous systems, okay? Now, we said from a theoretical point of view, and we saw that very well in the proofs, right? One of the key strengths of autonomous systems is the fact that if you have a scalar function v of x, dv of x over dx, which is dv over dx times f of x, can be written, as we said, v dot of x. All right? So we use that everywhere in the proofs and so on, right? The fact that if you have an autonomous system, if you give me v of x, I can give you v dot of x at any point. Right? And this allowed this kind of very elegant interplay of geometry and dynamics, which is at the heart of the basic Lyapunov theorems. Now, of course, you can see immediately if you have f and x of t, it's not going to be v dot of x. It's going to be v dot of x and t, right? Which means that at a particular point in the state space, you won't be able to give a given velocity, if you want, in v, unless you know time as well. All right? So the geometry is going to become more complicated, or less natural, if you want. So that's one way to see it, from the basic proofs of the fundamental Lyapunov theorems. We know that we relied heavily on this. Another way to see why it's going to be more complicated is to look at the next step from linear time invariant system, which is linear time varying systems. Okay? So let's look at a little example. It was chosen to be reasonably simple. You can make it even more natural if you want, as this one. This one was chosen just to be simple. So suppose we take a linear time varying system, so x dot equal a of t times x. And specifically in dimension 2, this linear time varying system, x dot is equal to minus 1, minus 1, 0, e to the 2t x. Right, so we're looking at the linear time varying system, right? So which, if we start with a linear time invariant system, of course, is the obvious step to look at non-autonomous systems. Okay. So let's look at this system, right? And again, we could conjecture that if the eigenvalues of a of t are always in the left half plane, then the system perhaps indeed is stable. It will go back to 0, right? That would be a natural first conjecture, right? How do I analyze the stability of this? Well, I look at every t, and if at every t the eigenvalues are in the left half plane, the system will tend to 0. Okay, that's a conjecture. Okay. Now, it's not always easy to prove conjectures, but sometimes much easier to disprove conjectures. Okay, so the point of this system shows that this conjecture is not true. Okay, so what are the eigenvalues of this system? Well, if you compute the eigenvalues, just get the diagonal here, right? You have a 0 here, right? So the eigenvalues of the system are just minus 1. Double eigenvalue at minus 1, right? So not only they are in the left half plane, but they're constant. Okay? So the eigenvalues don't even change. All right? So if the conjecture was true, well, the system would tend to 0, okay? However, of course, the system doesn't tend to 0. How can we see this? Well, because the system was chosen simple enough so that we can solve it, right? Of course, a lot of the point of all the stability analysis and so on is that you don't have explicit solutions, right? Or it's not easy to come up with explicit solutions. Otherwise, you would come up with explicit solution and see if it tends to 0 or not, right? In this case, it's very easy to solve it, right? You can first solve the second equation. So if you solve the second equation is x2 dot is equal to minus x2, right? So the second equation tells you that x2, well, let's do it in steps, right? x2 dot is equal to minus x2. And the first equation tells you that x1 dot plus x1 is equal to e to the 2t times x2. All right, so I've just rewritten these two equations. The second one, x dot equal minus x2. The first one, x1 dot equal minus x1 plus e to the 2t x2. Now I can solve this first equation, x2 dot equal minus x2. And what does it give me? Well, of course, it gives me x2 is equal to whatever it was initially, x2 0, okay, e to the minus t. So far, so good, right? So that tends to 0. However, the second equation tells me x1 dot plus x1 is equal to e to the 2t x2, which I've just computed. So it gives me x2 0 e to the plus t, right, 2 minus 1. So you see that the x1 equation is basically a low-pass filter driven by an exponential that blows up. So of course it blows up, unless x2 0 is exactly 0. Right? So this implies, so in this example, x1 tends to infinity and x2 tends to 0. Right? That's what this says. So of course, the state doesn't tend to 0. Okay? So here we have a very simple system, right, where the eigenvalues not only are in the left half plane but are constant, but the system blows up. Okay? So it's not true that if you take linear time varying system, you just have to look at the stability of each of the linearization and you'll be fine. Okay? So everybody understands this, right? This was one way to show why it was harder for non-autonomous system, just from geometry, right? And it's another way to show why it's harder, because even for a second-order linear system, we see immediately why it's harder. Okay? Now, this doesn't mean, by the way, that there's no way to analyze systems like this, right? So, for instance, and towards the end of the course, we'll give much more general results. Well, in the second part of the course, we'll give much more general results, okay? But for instance, you see what happens here is that the eigenvalues are -1, and the reason is when you take the determinant, right, you get the product of 0 by this thing which is blowing up, which gives you 0. Okay, so in a sense, when you take the determinant, you're kind of hiding this term. Okay. Now, you might wonder, well, suppose I take a system x dot equal ax, and I look at the eigenvalues not of A, but of the symmetric part of A. Okay? So assume all eigenvalues of the symmetric part of A. Remember A plus A transpose over 2. And sorry, it's really x dot equal A of t times x, of course, are less than some number, some constant, for all time. Okay? Just saying, just trying to get a hint of what kind of theorems could we get for linear time varying systems. Okay? So one theorem you can get, but again we'll do much more general things, is you start with this linear system, linear time varying system. You don't look at the eigenvalues of A because we know that doesn't work, right? But you look at the eigenvalues of the symmetric part of A. Okay? Assume all eigenvalues of the symmetric part of A are less than -2 lambda. Okay? Then x does tend to 0 exponentially with rate lambda. This constant, of course, is negative. Okay? Strictly negative constant. So suppose that not the eigenvalues of A, that we know that it won't work, but the eigenvalues of the symmetric part of A are all strictly less than some negative constant, then that will work. Okay. How can we show this? Well, basically we can use Lyapunov's idea, but without really invoking Lyapunov theorems. Okay. So how can we do this? Well, we're just going to pick a scalar function, which we'll call V. And the scalar function will just be x squared, x transpose x. Right? So here we're not using any Lyapunov theorem, but we're really using a Lyapunov idea, okay, of looking at a scalar and things like that, right? So we have V is equal to this, right? V dot can be written, so it's the derivative of a product of two terms, right? So it's x dot transpose x plus x transpose x dot. And therefore, we can replace this by its expression. So x dot is equal to ax. Okay. So we get x transpose times A transpose plus AX. Right? X dot is equal to AX. Everybody follows that? And what can we say given what we've assumed about the symmetric part of A? Remember we said when we have a symmetric matrix, we can bound it by lambda min x squared and lambda max x squared, right? So we know that all the eigenvalues of this are less than some constant. Okay, all these matrices are a function of time, right? This is A of t everywhere, right? But we know that this is less than some constant, which we called lambda, okay? So here we'll have minus 2 lambda x transpose x, right? Because the symmetric part is A plus A transpose over 2. Right? So this is the same thing as minus 2 lambda times V. And therefore, V, what do I have? I have V dot plus 2 lambda V negative. If I, right, I have V dot less than minus 2 lambda V. Which implies that V is stuck between 0 on the one hand because it's positive, and whatever its initial value was times e to the minus 2 lambda t. Right? If you had V dot plus 2 lambda V equals 0, you would have V equal V0 e to the minus 2 lambda t, right? So here you have less or equal. We'll come back to that, okay? Since I see some worried looks. We'll come back to this inequalities. And therefore, V, remember, is x squared, right? So it says that V converges to 0 with a rate of 2 lambda, so x converges to 0 with a rate of lambda, right? Which means the result, right? Okay. So in other words, we haven't used the Lyapunov theorem or an invariant set theorem or whatever. Anyway, we're dealing with a non-autonomous system. We haven't seen any, right? But we've fundamentally used Lyapunov ideas. You take a scalar, you differentiate it, and you see whether you can show things out of this scalar and this summarizing function. So here we show that V dot is less than minus 2 lambda v. Therefore, that v dot satisfies this equation. Therefore, v, which is positive, is also less than the shrinking exponential, which means that v tends to 0 exponentially with a rate 2 lambda. And since v is the square norm of x, it means that x tends to 0 exponentially with a rate lambda. Yes?
Can we then say that for a linear time invariant system, if the system is stable, then the eigenvalues of the symmetric part are definitely negative?
No. No, actually, it's a good point. And actually, that's what we just saw when we saw Lyapunov theorems for linear time invariant systems. We said it's not true that if you pick p equal identity, then q will be negative definite. Okay. So here we're proving the other way around, right? We're proving that if you have a system, so that could apply to a linear time invariant system too. If you have a linear time invariant system whose eigenvalues of the symmetric part are all negative and the system is stable. Okay. But it doesn't show the other way around because actually the other way around we know that's not true. Good question. Any other question apart from this inequality I'll come back to. Okay? So this is just one theorem, okay? It's just to say, there's no reason to put your arms up and despair, right? There are still things that you can say about these linear time varying systems. And here we try to exploit the fact that we thought we had a hint about the mechanism why this didn't work, namely that you multiply this 0 by this exponential. Okay, and therefore we took the symmetric part first. Okay? So just a quick remark about this, right? We said we have this equation v dot plus 2 lambda v less than or equal to 0. Therefore, v is less than v e to the minus 2 lambda t, right? So, of course, if we had equal 0, then we could say v is equal to v e to the minus lambda t, okay? So the trick is simply to say, if you're not familiar with this, right? So we have this equation, v dot plus lambda v less than or equal to 0, okay? So we can write this, of course, as v dot plus lambda v is equal to some r of t, some function r of t, which is negative or 0, right? We haven't said anything new. Instead of saying v dot plus lambda v is less or equal to 0, we call it some r of t for some initial condition, right? And that r of t is negative. Okay, so far so good? But if you say that, then of course you can now view this as a linear system driven by r of t, right? And therefore, v of t will be v at t equals 0 e to the minus lambda t plus a convolution integral, right? Sum from 0 to t of e to the minus, there's a 2 lambda, sorry. Just for e to the minus 2 lambda t plus a convolution integral of e to the minus 2 lambda t minus tau r of tau d tau. Right? Just have a linear system with an input. Okay, so you can write it this way. And this, of course, is negative. Why is this negative? Because r is negative and the exponential is positive. So that's how you get this inequality. Right? So in this case of so-called differential inequalities, right, you know it's the same result as the equality plus driven by something negative, right? And so since it's linear, the effect of the negative thing is very easy to compute explicitly. And of course, once you have this form, it's the integral of an exponential, which is positive, times something negative, so it's negative. Okay? So that's why we went immediately from here to there. And of course, the other thing that allows us to conclude is that we know that v is positive. Okay? Otherwise, it could become negative or whatever. Here, we know it's stuck between 0 and something that shrinks to 0. Okay? Questions about that? All right, so this was kind of a side remark on saying what kind of theorems could we get, for linear time varying system. And towards the second part of the course, we'll get much more general theorem, which will apply to linear time-varying systems and nonlinear non-autonomous systems using a little similar ideas. Questions about this? Okay, so for the moment, we've motivated why it's harder, and as a ray of hope, we also gave an example of what kind of theorems you could get. Okay. Now, there's a kind of a long chapter 4 because there's lots of literature on non-autonomous nonlinear systems, and there's even, of course, much more than what is in chapter 4. What we're going to pick out of there is one particular theorem, which is particularly simple and which has many applications for non-autonomous systems, but also for adaptive control and so on. And this theorem is called Barbala's lemma, and it's really a theorem in functional analysis. It has nothing to do, in a sense, with Lyapunov theory. And at the same time, it applies directly to Lyapunov-like ideas for nonlinear systems, nonlinear, non-autonomous systems. Any questions? Okay. So let's talk about this. Okay, so it's section 4.5, I think, right? So it's a Lyapunov-like stability analysis of nonlinear, non-autonomous systems, and the result that we'll focus on, again, there's many results in this context, but a particularly simple result we'll focus on is what's called Barbala's lemma, which again is from the 1950s, and it's a result in analysis. Before we get into Barbala's lemma, I'd just like you to think a little about properties of functions of time and their derivatives. Okay? The same way that, we said, well, we have different forms of stability and we have to be precise because they correspond to very precise practical questions. Here it's one point where we have to be precise, or at least aware of the fact that we have to be precise, not to jump to conclusions too fast. So let's just call it asymptotic, meaning at t equal infinity properties of some smooth function g of t and its derivative g dot of t. So the first question is, suppose that you know that g dot, let me put some color here. So suppose you know that g dot tends to 0 as t tend to infinity. Does this imply that g of t tends toward a limit as t tends to infinity? Right? So you have a function, a nice smooth function of time. Okay, derivative exists, second derivative exists, everything is nice and smooth. Is it true that if the derivative tends to 0, the function tends towards a limit? Well, it's certainly not true, for instance, that it tends towards a finite limit, because if you just say take log t, right? If you take g of t equal log t, right? The derivative, of course, g dot is 1 over t, which tends to 0, but log t is going to tend to infinity. Okay. So that's a limit, right? It's not a finite limit. So it's certainly not true that it tends towards a finite limit. Okay. Now, but that's kind of almost a trivial remark, okay? So let's pick a function that stays bounded, but has the same property. So suppose we take sine of log t. So what does sine of log t looks like as a function of time? Think of it. Well, basically, it's a function that gets more and more boring, right? Like some classes. So it starts, doing lots of things, right? Being very excited, and then, it gets flatter and flatter. But it never tends anywhere, right? Right? The g dot is going to be 1 over t cosine, right, of log t. So g dot tends to 0, of course. This is g of t. G dot tends to 0, but the function keeps drifting, right? Slower and slower. It doesn't tend anywhere. Right, so that's a case where g dot tends clearly to 0. G remains bounded, right, between -1 and 1, but doesn't go anywhere. Okay? So in other words, this is not true. Okay, this implication is not true. And notice, we didn't have to make a very complicated construction with spikes getting further and further. I mean, we didn't have to make a page of construction to get this counterexample, okay? So if you think of it, linear systems respond like exponentials, right? And sinusoids, right? So it's not very complicated to make up some slightly nonlinear combinations of linear system which gives you sines and logs, right? So it's a counterexample, but it's not a contrived counterexample. It's not a big deal to find something like this. Yeah. So what about the other way around? So what about, is it true that if you have a function that converges to a finite limit, then, so let's take the same structure here. So x tends to a finite limit as t tends to infinity, okay? Is it true that it implies that g dot of t tends to 0? Well, here you have to get a slightly more complicated counterexample, but that's not true either. Okay, so for instance, if you get g of t, the idea is that you put a decreasing exponential times something bounded but reasonably active, like sine e to the 2t. Right? Suppose you take this function. If you differentiate it, right, we won't do it completely, but if you differentiate it, you'll see you'll have a term which will be minus e to the minus t times sine this, so that will be fine, okay? But then you'll have another term which will be 2 e to the minus t e to the 2t times something, right? So it will be e to the plus t times something. And so you see that this term will blow up. So basically, the derivative doesn't tend anywhere. Actually, it's getting worse and worse. But the function tends to 0. Okay? So neither of these implications is true. It's not because g dot tends to 0 that g does tends to finite limit or whatever, and the other way around is not true either. Okay? Third question. If g is lower bounded, if g dot is always negative, is it true that g of t tends to a finite limit? Well, yes, that's true. We've used that. Okay, we've used that when we showed the asymptotic part of Lyapunov theorem on asymptotic stability. You said start with a trajectory. We know we tend towards a limit. Capital L is this limit. Can this limit be anything other than 0? Remember? So we use that as a basic result in analysis, right? If you have something which is decreasing and lower bounded, it tends towards the limit. So that is true. But the other two aren't. Okay. Okay. So what is Barballa's lemma? Well, it's a result that tries to make point 2 more precise. In other words, it says, suppose I know that g of t tends to a finite limit, as t tends to infinity, of course, and I add some extra condition, then this implies that g dot tends to 0 as t tends to infinity. In other words, Barballa's lemma says in this question here, what extra condition should we add so that it does imply that g dot tends to 0? So of course, there's many answers to that. Okay, we could add the condition that g dot tends to 0. It would not be very interesting, but all right. We could add actually the condition that g dot tends towards some finite limit. Actually, that would be would have to be 0. Okay. But in Barballa's lemma, we give a condition which, in a sense, is often easier to verify using Lyapunov-like tools, which is that g double dot is bounded. Okay. So if we add the condition that g double dot is bounded, then it will be true that if g tends towards a finite limit, then g dot will tend to 0. Okay? What do we mean by bounded? We mean there exists some alpha such that for any t, g double dot of t is less than alpha, right? That's what bounded means in absolute value. So one possible express condition is that g double dot is bounded. And then this will imply that g tends to 0 as t tends to infinity. Now, if you think of it, this directly gives us a sort of Lyapunov theorem, a kind of a Lyapunov-like theorem, which is also called Barbaro's lemma because it's such an obvious or such an immediate application of this. So suppose you start with a non-autonomous system, x dot equal f of xt, and you somehow find a scalar function, v of x and t, which is lower bounded, perhaps by 0, but in general lower bounded. Doesn't really matter anyway because we're going to take the derivative. Such that d over dt of v is always negative or 0 along all trajectories. And such that d square over dt of v is bounded. Then d over dt of v tends to 0 as t tends to infinity. So that's the result. All right. So what the theorem says, we're going to prove this. You'll see it takes a second. Theorem says if you can find a scalar function for this system, which is lower bounded, for instance positive, whose derivative is always negative, so that scalar function keeps decreasing, and whose second derivative is bounded, okay, then the first derivative tends to 0. And that's the result. Okay, so that's what the theorem says. How can we show this? So we haven't shown this. You have a proof in the book, a slightly more general proof in the book. But assuming this result, how can we show this? And that's why I'm saying it's also called Barbaro's lemma, because it's really an immediate application of this. Well, if we have a scalar function v whose derivative is always negative, right? Then we are in this case. Okay? It tends towards a finite limit, starting with any initial condition. Right? Now we also know, of course, speaking g of t equal v of x of t and t, right? We also know that if it tends towards this finite limit and its second derivative is bounded, then the first derivative tends to 0, okay? So the proof is just for a particular trajectory, a proof of that theorem, you just apply it to g of t, which is v of x of t and t for some particular initial condition. Okay? So that's why I'm saying it's an immediate application, and it's also called Barbaro's lemma, right? Out of the first two conditions, you get that v dot, you get that v tends towards a finite limit, and out of the third condition, you get that v dot tends to 0. Okay? So that's an immediate corollary of this. Okay? Questions about that? So of course, that's your result. Okay, the result is v dot tends to 0. So somehow you should construct v so that this works. And the result is interesting, right? If you spent a lot of time constructing v to find v dot equals 0, then of course the result that v dot tends to 0 is not interesting, right? Or if you built up v so that v dot is equal to 2e to minus t, then it's not interesting either to know that v dot tends to 0 because you knew that also, right? So typically, saying typically, right, it doesn't have to be always the case. You're going to choose v such that v dot is something like minus the error square. Okay, perhaps the trajectory tracking error or the error in the estimate, the estimation error in the nonlinear observer or something like that, right? You're going to choose v such that somehow v dot is minus your error term square or minus the absolute value of your error term or something like that, okay? So that applying the theorem and therefore knowing that v dot tends to 0 tells you that the error tends to 0, right? And of course you put a minus sign because you want v dot to be negative. Right? So typically it's going to be that, okay? It may be absolute value, it may be to the power 4, but typically it's going to be something like that. Okay? Also typically, not always, but typically the first two conditions are going to imply the third. Okay? First two conditions. Just to be clean, let's just call it d over dt of v, otherwise it might be a little, rather than v dot, okay? It might be a little confusing at this point. So v lower bounded, time derivative of v is less or equal to 0, imply the third, namely that v double dot is bounded. I'm saying typically, okay? Why? Because if you think of it, you know, v might be, for instance, something like a sum of the squares or some powers of the states, right? And so knowing that v is bounded says that each of these individual terms in the sum is bounded, which means that if you compute v double dot, it will contain all these state terms, and you'll know that each of them will be bounded. Okay? Now, I'm saying typically because you might have 1 over something or so on in some cases, right? But typically that's what's going to be the case. So out of the fact that v is bounded and decreases, out of the fact that v is lower bounded and decreases, you'll show that v is bounded, period, lower bounded and upper bounded because it can decrease. This will in turn imply bounds on the states, which in turn will imply bounds on whatever is used to compute v double dot. Okay? So typically that's the two things you'll have. You will choose v such that its derivative is minus the error square. And the third part will come automatically from the first two, but you still have to check it. Okay? And so that will be the game, right? Designing a candidate for this Lyapunov-like function. And typically, of course, in a closed loop setting, so a choice of control law or a choice of adaptation law or something like this, such that for the closed loop system, these things are verified. And of course, we'll see many examples of that. Questions about that? Questions? Yes?
Have you used Lassiel invariant cat theorem for this system?
Okay, so not the one we showed, okay? Lassalle actually wrote a paper in the 70s deriving some variation, some much more technical variation of the invariant set theorem for non-autonomous systems. Okay, so you could use that, and as I said, there's many theorems related to this. Okay, we'll use this theorem. Any other question? Okay. Sure. Yes.
Is there some intuition for choosing the error beyond that it might make B suitable? So like.
Yes, we'll talk a lot about that. We'll talk about that. Actually, we're going to talk about it almost right now at the next lecture. But notice also that in a sense, I shouldn't say Lyapunov is still lurking, right? But all what we've said were things done after Lyapunov, but still very much based on Lyapunov insights. Okay. Some variations because problems get more and more general and more technical. Okay, but still very much based on Lyapunov insight of the scalar summarizing function that decreases. Okay. Okay. Including, of course, what we said about linear time-varying systems. Okay. Any other question? So for the moment, the second half of the course will give more tools, but for the moment that's where we'll stop for analysis tools. Okay, we're going to start talking about design, okay, about control system design. Okay, and we'll give more analysis tools and their control applications, in the second part of the course. Okay. So we're going to jump a little in the book to chapter 7. And we'll come back to chapter 6, which is an important discussion in nonlinear control, but it's rather technical. So we'll come back to chapter 6 a little later. And basically, we're going to talk about robust control of a nonlinear system in some specific context. And typically, we're going to consider n-dimensional version of F equal ma kinds of problems. So if you have a scalar x, we're going to look at system corresponding to differential equations of the form f of x dot x to the n minus 1 and t plus b of x dot x to the n minus 1 and t times some scalar control input. So let's look at these systems from this moment. These are scalar systems, kind of extension of F equal ma, but kind of n-dimensional extensions of that. And apart from being scalar systems and single input systems, what's one of the main special things about these systems? Why this is not any n-order system? Well, we'll come back to that in a sense. That will be the whole story about chapter 6. But what's special here is that the state of the system is simply a scalar and its derivatives. Right? And you can write everything in terms of that, and you end up with a scalar nth order differential equation. Right? So in a sense, it will be the central question in chapter 6, how general is this? When can you take a system with its state and somehow transform the state so it becomes a scalar in its derivatives? But we'll come back to that. Still, you can immediately see, just starting from there's lots of real physical systems that look like this, right? F equal ma, you can add motor dynamics, it will still look like this. I mean, there's lots of systems which are going to look like this. N-dimensional version, rigid robots are going to look like this. Okay. So, rigid robot, aircraft, spacecraft, lots of things are going to look immediately like this. And why am I calling this robust control? Because, of course, if F and B were exactly known, let's assume that this B is strictly positive, okay? So we know at least in which direction we're pushing. Okay. But so what I'm going to say is really coarse. Okay, it's just to tell you why we're calling this robust control, because that's not what we're going to do. Okay, but if we happen to know exactly BF and exactly B, right? And we had some questions. So, for instance, we had a trajectory tracking problem with some error, which we would call x tilde, which would be the difference between the actual and the desired. Okay? And this tracking error we would like to tend to 0, for instance. Okay? So we could have this system, and we'd like it to follow a particular trajectory. And we would have a trajectory tracking error, which we can call x tilde, which is the difference between the real thing and the desired trajectory. And we would like this to tend to 0. Now, suppose F was exactly known, B was exactly known, okay? Then something really coarse, okay, one could do is call this entire quantity small v. I'm saying small because it has nothing to do with the Lyapunov function. So small v, right? So we would have x to the n equal v. So that's a nice linear system. We could design v any way we wanted. And at the end, we could solve for u. Right? Right? If F and D were exactly known. We could say, forget about all this thing, right? Let's just call it V. It's a right-hand side. I can design, using measurement of the state, whatever I want with this. Gives me V of X and T. And then I solve for U, and that's what I apply to the real system. Now, of course, real systems are not like that. You don't know F exactly. You don't know B exactly. Okay? And depending on the system, they may be quite far away from that. Okay? So, for instance, if you pick a baseball bat, okay, then the dynamics of your arm, or if a robot picks a baseball bat, right, the dynamics of the arm with the baseball bat is very different in terms of its parameters than without the baseball bat, because the baseball bat is of weight and size similar to those of the arm itself. Right? So it won't be at all the case that you know the dynamics whether you have a baseball bat or not. Okay? You need to know much more about the bat. Okay? Similarly, as you know, people are trying to find oil in deeper and deeper region of the ocean with sometimes rather unpleasant consequences. And one of the many problems linked to this is that you have to maintain these oil platforms. Okay? And if you think of an oil platform somewhere off Norway in the North Sea, right, maintaining it in the winter is not very pleasant thing to think of, especially if you think that, you know, divers are the default, you know, the default choice to do that. Okay, so of course one would like to build underwater robots that do that instead of divers because it's a very dangerous work. Okay, maintaining things underwater, right? Now, if you think of it, right, if you have an underwater robot or which is trying to do some work in contact with an underwater piling, you know, somewhere in the North Sea in rough weather, okay. So if you suppose you're trying to do maintain some contact, okay, with the piling, it means that, and there's some current coming here. So when you are here, you have the full current. When you're behind, you have no current, and when you come back, you have again the full current. Okay. So you know, first of all, you know very little about what this current is, and of course, even if you knew, it would be very complex hydrodynamic equations. All right. So the model you're going to use for that is going to be quite far away from the real thing. Okay. So what we're going to look at is the case where, okay, so you have F, you don't know, but you have an estimate of F that you do know, some simplified estimate, okay? And that estimate is less than some f of xt. So in other words, this quantity you don't know, and these two quantities you know, the estimate and how bad or how good can it be. Right? So for instance, if we take, you know, our very, very simple model of an underwater vehicle we saw in the first class, you know, v dot plus v absolute value of v equal u, right? Well, you can say this v absolute value of v is modeling my real underwater dynamic with an error of perhaps 40%. Right? So you're going to know that your model is v absolute value of v, and your bound will be 40% of that. Okay? So, or similarly, if I take the robot with a baseball bat, you're going to say, well, you know, most of the mass parameters I'm going to see in this robot are going to be within a factor 2. Okay. So, and of course, a similar equation for B, okay? So similarly, B is going to be known within certain bound, okay? And with a known worst case error, if you want. So that's the setup, okay? We're going to try to deal with these systems where we assume that, of course, we don't know the system exactly, but we have some estimate, which, depending on the problem, may be reasonably accurate or could be quite far off. And we're trying to do our best to achieve this trajectory tracking error tending to 0. Okay. And in the process, the first thing we'll do is try to answer your question a little better about what should we pick as an error signal. Okay? And that's what we'll do next time.